Dudley Observatory, founded in 1852 by a public-spirited group of citizens in Albany, has played a long and colorful part in the growth and development of American astronomy. Over the years, the observatory has been involved in a number of fundamental scientific discoveries. Benjamin Gould, Dudley Observatory's first director and founder of the Astronomical Journal, purchased a Scheutz difference engine, the first stored program digital computer. The Scheutz engine was used in the early years of the observatory for the calculation of the first set of astronomical refraction tables. In 1892, a new observatory and director's residence was built on Lake Avenue in Albany. It housed the Alcott Meridian Circle Telescope, an instrument used to make precise measurements of stellar positions. Louis Boss, fourth director of the observatory, realized while surveying the 49th parallel between the United States and Canada that the largest single source of error in his survey was the uncertainty in the fundamental position of the stars. This study, continued by Benjamin Boss, culminated in the publication of the Boss General Catalog in 1937. It was the first high-accuracy catalog of large numbers of stars in both northern and southern hemispheres. Space research has been emphasized in recent years under the observatory's next director, Curtis L. Hemingway. Under his direction, the first cosmic dust collectors were constructed and subsequently flown on balloons, rockets, orbital space satellites, and manned spacecraft. Scanning electron microscopy is used to study impacts of hyperballistic micrometeorites on targets exposed on spacecraft. In 1970, the decision was made to construct a major new observing instrument, a fully steerable, computer-controlled radio telescope. The stimulus for the observatory's decision came from an offer by the Carnegie Institution of Washington to give the observatory its 100-foot diameter parabolic reflector. The logistical problem of moving the 100-foot reflector from its original location in Maryland was resolved in the spring of 1971, when Joe Urquhart and a contingent of 7 SUNY students disassembled and shipped the dish to its new location, a sheltered valley in the Adirondacks near Lake George, 1 hour north of Albany, was chosen as the location for the telescope. A 200-acre tract of land in the valley was given for use as the site of the radio telescope by Mr. and Mrs. Howard LaRose of Lake George. After the shipments arrived at the Lake George site, the painstaking work of reassembling the jigsaw puzzle began. The components of the telescope, which had been marked before disassembling, had to be carefully sorted before the job of reassembling could begin. The telescope itself is a composite of steel and aluminum, consisting of an inner toroidal ring constructed of high-strength, large-diameter steel tube and 32 radial rib trusses made of aluminum. This kind of composite construction combines high strength and stiffness in the center section with low overall weight for the telescope. By way of comparison, the 140-foot diameter telescope of the National Radio Astronomy Observatory has a total moving weight of in excess of 2,600 tons, while the total weight of the Carnegie paraboloid is less than 15 tons. One of the most important considerations in the rebuilding of the telescope was the requirement that the paraboloid have a very high accuracy. In order for the instrument to be usable at wavelengths as short as 6 centimeters, the maximum deviation of the surface of the paraboloid from a perfect paraboloid could be not more than 1/8 of an inch. A precision theodolite was used to carefully align the rib trusses as they were assembled to ensure that the dish would have an accurate shape. When the students returned to their classes in September, the paraboloid had been reassembled and was ready to be mounted. In the fall of 1971, work on the foundation of the radio telescope began. The site chosen for the telescope had one serious disadvantage as far as the foundation was concerned. The water table in the area was only 3 feet, while the frost line went as deep as 5 or 6 feet during the winter. A conventional foundation would have resulted in severe frost heave. The solution was to build a massive 240-ton base for the telescope, which rested on a mound of compacted crushed stone, well above the water table. In the summer of 1972, work on the support tower of the telescope was begun. The 50-foot high tower is conical in shape, providing the lightest, strongest, stiffest structure. The tower is composed of 12 panels made by an outside steel fabricator and assembled by the observatory staff. The 5/16 of an inch thick panels, although relatively flexible individually, formed an extremely rigid, stiff structure when fully assembled, bolted, and welded. The tower, 20 feet wide at the base and 12 feet wide at the top, provides ample working and storage space for the operation of the telescope. The 5 floors inside the tower yielded over 600 square feet of floor space. The entire structure rests on 72 anchor bolts cast into the foundation. This not only simplified the construction of the tower, but also allowed the tower to be leveled after it had been erected. The cylindrical section, the top floor of the tower, is the location of the power units for the hydraulic motors which drive the telescope. With the completion of the tower, one engineering problem remained: the problem of designing and building an altitude-azimuth drivetrain capable of accurately pointing a 15-ton dish 1/3 the length of a football field. Its angular error had to be smaller than the apparent diameter of a basketball as seen at the distance of a mile. The acquisition from the U.S. Navy of a gun mount salvaged from a heavy cruiser solved our azimuthal drivetrain problem. The gun mount, stripped of its armor and guns, provides a very stable, precise, rotating platform. The final mechanical element in the telescope is a torque tube interface, the link between the bearings, spaced rather closely together on the gun mount deck, and the telescope. The torque tube design was chosen because it's a relatively light and extremely stiff way to support the dish structure. The torque tube interface incorporates twin counterweights, so that in its finished form, the dish is balanced in all orientations, making the task of the drive motors easier. On November 6, 1973, the day scheduled for the cranes to lift the telescope and mount it, the observatory declared a holiday and invited the staff and interested members of the community. The day chosen proved to be rather windy, and the paraboloid, as it was raised, filled with wind like a gigantic sail. The strong gusts caused some concern to be felt, since any further increase in the wind speed might have made it difficult to proceed. The paraboloid's large surface area, so useful in collecting radio radiation, proved to be a handicap during the lift, as the dish tugged at its restraining lines, seeming to resist the crane crew's efforts to position it. As the crane crew slowly guided the paraboloid into position, its sheer physical size became apparent, and the instrument finally began to look like a radio telescope. Finally, with the tightening of the last bolt securing the telescope to the torque tube interface, the last major mechanical component of the telescope had been completed. Since then, the telescope has been turned into a working instrument. A residence trailer and laboratory have been added, as well as a powerhouse with an auxiliary diesel generator. The telescope is equipped with a low-frequency receiver sensitive to long wavelengths where non-thermal radio sources like pulsars produce most of their radiation. In the telescope's control room, the signals received by the radiometer are recorded and analyzed. At the control console, the observer types in the celestial coordinates of the radio source, in this case Virgo A, a bright radio galaxy. The Frank L. Fulham radio telescope is being used in a unique series of experiments probing the nature of a relatively new class of astronomical objects, perhaps best exemplified by the pulsars, pulsed coherent emitters. Of all the stars in the night sky, possibly the most beautiful are the bright, hot blue stars. It is perhaps ironic that these stars, the youngest in the galaxy, live the shortest lives, often ending them in violent explosions, briefly lighting the entire galaxy. One of the most spectacular of these supernova explosions in recorded history occurred in a star several thousands of light years away in 1054 A.D. The object we know as the Crab Nebula is the remnant of that explosion. Attention is focused in recent years on the two stars in the center of the nebula. Astronomers had speculated that the fainter of the two might be the leftover core of the star that had undergone the supernova explosion. It is now known to be a pulsar, or a rapidly rotating dense neutron star. An intense beam of radio emission, focused perhaps by the strong magnetic fields of the neutron star, appears to blink or pulse as the pulsar's rotation sweeps the beam across our line of sight. Attempts to delve into the origin of the pulsed emission have been stymied by dispersion, a distortion imposed by the interstellar plasma. Free electrons in the clouds of gas and dust along the path the radio pulses must travel severely affect the propagation of the radio waves, slowing down low-frequency waves much more than high-frequency waves. A radio pulse produced by a pulsar can be thought of as consisting of a series of components at different frequencies, all emitted simultaneously. As the pulse travels across interstellar space, the lower frequency components will lag after the higher frequency components. As a result, the pulse, as seen many light years away, will be many times fainter and of much longer duration. Although we've learned much about pulsars in the past decade, the pulse emission mechanism is still largely a mystery. A fresh approach to this problem was initiated by Ivan Linscott and his collaborators Joe Urquhart and Noble Powell. The approach involved using the latest LSI digital technology to implement digital coherent processing of radio signals. With support from the National Science Foundation and private donors, the group has developed the hardware and techniques to use these signal processing ideas in the study of pulsars and other pulsed radio phenomena. The heart of the system is a very fast Fourier transform, or FFT, processor, built by General Electric's Electronics Laboratory in Syracuse. The processor is interfaced to a general-purpose mini-computer with mass storage and graphics capability. Signals captured by the FFT spectrometer are displayed on an oscilloscope in real time, showing the noisy cosmic background radiation. To illustrate just one of the many capabilities of the FFT spectrometer, a dispersion-broadened pulse has been simulated by an oscillator rapidly sweeping in frequency. The frequency spectrum of the artificial swept pulse is shown on the screen. Its energy is spread out over the entire band, just as a pulsar's radiation would be. After coherent processing, we see in the upper trace the resulting dispersion spectrum. Its energy is packed into a few channels, making signal detection relatively easy. Recovering weak, natural pulses against a background of strong cosmic noise is much more difficult, since often the signals are hidden in the noise. As an example, here we see a record in which the signal is completely buried in the noise. After coherent processing, however, the pulse can be clearly seen. This ability to recover coherent pulse signals, often in the orders of magnitude fainter than the noise, makes the FFT spectrometer a powerful tool in our attempts to study and understand pulsed coherent emitters. Dudley Observatory's FFT spectrometer represents a new technological development, the fusing of modern digital technology with radio astronomy to permit for the first time the coherent analysis of radio signals. Historically, such developments have resulted in unexpected new discoveries, and today, perhaps, we stand on such a threshold.